Hello everyone, this is Mohsen Saraj from the Ozen Engineering team. Today I want to talk about modeling power plant, a full cycle of power plant using the Flownex software. Basically, Flownex it is like a 1D program that helps us to determine pressure drop of the flow and perform heat transfer analysis to finding the temperature within and between the connected components such as pumps, compressor, turbines, tanks, pipes, valves, or heat exchangers that we're using in power generation systems, and we can do steady state analysis and transient analysis. This is a schematic of a power plant with combined cycle, and by combined cycle I mean that we have the gas turbine for power generation, and we have another turbine which is a steam turbine that basically uses the heat from the exhaust hot gases from the gas turbine, use it for producing steam. Here, as you can see that we have the system for steam generation, that it is a boiler basically, and also water for that from condenser that feed to the boiler system. So generator in this power plant basically receive two power, one output power from the gas turbine and another power from the steam turbine. So that's why we expected to see more efficiency and more output power, total power from these cycles for the power plant. In Flownex, okay, basically what we have two uh, thermodynamic cycle. One is for gas turbine that uses that models with Brighton cycle, and another one for steam turbine that it basically based on the ranking system. And boiler steam generation and the cooling water circuit that we have, Phelonics has separate tutorial on that for that. The good things is that for the design and analysis we can run steady state and transient analysis, and we can have a calculator to find the amounts for the efficiency, cycle efficiency, and total output power. And in this way, we can run the model for, for example, different inputs that we can have. Say that, for example, changing the fuel, changing the fuel gas that we have. Okay, changing also the say that for uh, atmospheric condition that we have. It depends if it is a rainy day or non-rainy day, and what information we have for the for the air intake that we have here. These are and also for just root cause analysis. Okay, just we find it out if in different scenarios, okay, what we can have. So for example, for different load change scenarios, okay, we can run transient analysis for that. Also for, as I say, that different ambient conditions for the state, to see that how that affects the production of the power plant and the efficiency of the cycle. Let's see that what main components we use in the Fellow network in Flownex model. First of all, we need tanks that we have tanks, we call it two-phase tank, that we're going to use it in condenser tank and also the boiler drum. Then we have the compressor and the gas, the turbines that we'll be using for gas turbine system and steam turbine system. That we have pump, for example here for feed water pump it could be variable speed. We can have other types of the pumps in Flownex. We have heat transfer element, okay, that if here we use it when we wanna uh, use the heat from the hot exhaust gas from the gas turbine, and then variety of the pipes and also some elements that we have it for model the resistance to the flow uh, within the pipeline, and if there is any loss that we can model that. These are the main model, the main components that you're going to see in Flownex model. Let's now look at the model inside the software. Flownex model. Okay, this is the Flownex model for the combined cycle of the power plant. This part it is for the gas turbine. That you can see that basically we have air intake, we have compressor, turbine, and here this is the heat transfer element, it is flame, and we have here for the increasing the pressure and gas, with here pressure and here is the temperature. So this is the air intake coming to the compressor, and then after that going toward this flame section for the combustion, going back to the and going back to turbine and the compressor are connected with the shaft, and after that we have the hot exhaust gas that will be sent to boiler, or we call it here heat recovery for steam generation. Okay, this is what you're going to see here. Okay, hot gas. Okay, this this is the line for that, and it will the exit and vented out to the atmosphere. Before that, okay, we have the steam turbine. As you can see here, this is the steam turbine that it has this line for the steam that generated within this system, that basically for the steam cycle we have one two-phase tank which is for boiler for producing the steam. So, and the way is that it received water from this pump, okay, that coming through these lines, and as you can see between the pipeline from the hot gas exhaust gas from the gas turbine, and here we have thermal connection, okay, that if you look at here, okay, we have these tubes that these are belongs to a boiler for using the heating from the hot exhaust gas and producing steam, as you can see here. And if you check the material here, you can see that here we have two-phase fluid, general, and it is water. And if I want to see what is that, okay, for two-phase flow, okay, we can have the diagram for entropy in terms of the pressure, temperature, and the other things like enthalpy. Okay, for example, if we go for pressure versus enthalpy, you can see that where we have the different regimes for the two-phase flow, where we have subcooled regime and where we have the superheat region, and here we have the, as you can see, we have the two-phase flow. If we go for temperature versus enthalpy, again you can see that here we are in the region for the two-phase flow. This is for subcool region and this is for superheat, and so on for entropy or whatever. So we have two-phase flow for these pipes, okay, as you can see, and these are connected to this drum. This is the drum that basically it is like a, we call it a two-phase tank, and same material, it is a two-phase hot water. And if you look at the temperature of the hot exhaust gas from the gas turbine, okay, you can see that it is the gas turbine that we have it. And if you look at the pipeline, you can see that here this is mixed fluid, okay, because it is a product of the combustion from air, mixing of the air and the fuel. That the fuel here is the natural gas. Okay, so let's see what is the combination of that. So in Flownex, okay, we have a variety of models for mixture. It could be gas mix, it could be liquid mix, and then a combination of the liquid and gas, or particle and liquid, okay, that we have it. So here, as you can see, we have a mixture of argon, methane, carbon dioxide, water, nitrogen, and oxygen that we have it here. So we have one pipeline that after the gas turbine, this product of the of the fluid, operating fluid after at the from the outlet of the turbine. You can see that the temperature, it is almost 860, okay, for example, and as give heat, okay, to the steam, to this uh, pipe network from the boiler, okay, gradually its temperature reduced from 860 to 734 to 600, and for the exit line, for the exhaust line to ambient, it is 400 degree, that you can see that here. So and back to the gas turbine cycle, okay, this is what we have from the fuel, okay, as you can see at the beginning it is 4 kilogram per second, okay, and here we provided it by mass source, and these are the composition of this mass source. So for this example, we just consider a simple case that we have only methane for this composition of the gas fuel for that. And for rest of the cycle, for the steam generation, in this part it is for the condensation that provide cold water for producing the steam to from in the boiler. So here you can see that, okay, if we come here, okay, we have the steam after being used in turbine for producing the power, it just goes to the another two-phase tank that it is now, it is for the, we call it condenser tank, that we have it, and then it will be sent by feed water circuit feed water pump to the this boiler drum. So these are the main components that we have. If I look at that, for example, look at this two-phase tank, I can come here to the container. Okay, look at this is the two-phase tank, and for the compressor and turbine, okay, and also pumps. Okay, this is the component. For the compressor we have turbines, and also we have this component, variable speed component for the pumps. And we have variety of pipelines here. It is simple pipe that we see it here, and we can model the resistance and loss in the pipeline by here that we have it custom losses. Okay, this is fellow resistance that being used here. Here in the pipeline for hot exhaust gas, this is the fellow resistance that we model that. And another loss that we can have here, and another one, it is to calculate if we want to apply the restriction. Okay, it is like changing the diameter, or basically if we want to close or open suddenly a pipe. Also we have generator that it has calculator for finding how much is the efficiency and the total power that it receives from gas turbine and steam turbine. So, and this is the script, simple script. If you double click that, you can see that these are the formulas that used for calculation of the efficiency and the total power, and this, and here also if you click here, okay, you can find the uh, you can find the list of the inputs, parameter and outputs. So I already initialized this model. This model is provided from by Flownex team. So I at first running this for a steady condition. You can see that now we have calculation for the for overall efficiency and for the total power, and we have information also that what is the output power from the gas turbine and how much is from the steam turbine, and also some calculation, okay, for example for the air intake, as you can see that how much it is, and also this magnitude is constant, uh, that it is from the governed by this boundary condition here for now, and also the range of the temperature changing of the hot exhaust gas that's being used for steam production, and the temperature for the exhaust here. So this is what we have so far from the steady condition. If I click on the boiler, okay, boiler drum, and look at the results, if you check the here the heat source, you see that we have the negative values. It means that although we are using the we cover some heats from the hot gas pipeline. Okay, but we need here more. So uh, I'm going to use uh, that designer here, that with the goal that to reduce this energy source to zero. In this way, we have much efficiency regarding to the heat transfer in the boiler system. The designer that it is here, if you go to the configuration and check the designer setup, basically if you have here, this is for the boiler drum, and I want to make this one and set the value to zero. So this is the target for us. We put this constraint here, and if you look at here, okay, this is the pressure, this is the boundary condition, and the pressure for this boundary condition that applied to the pressure drum, to the boiler drum, and it can be changed in the range of 2500 up to 2800 kilopascal. So if I run this designer and see what's happening, okay, can we optimize the boiler system that we see zero energy sources? So it go to the iterations to find the best solution for that by changing the boundary condition here, the pressure boundary condition here. Okay, you can see that it is almost zero, and if you check the console, okay, you see here, you can see that we already found the solution, converged solution, which is good. Okay, so this is what so far we have. Okay, now let's run the transient simulation. For the transient simulation, we just consider these are the graphs that already created for the output power of the steam turbine and output power of the gas turbine. You can see that, and you can see maybe changes here during the transient simulation that we have. Check these values for the output power and for the gas turbine and for the steam turbine. You can see that it is changing, and the total output power. So 17.1. Okay, and let's see the graphs. Now we have 6 second, 7 second, 17.2 megawatts, and you see the output power for the gas turbine is almost constant, but the steam turbine is increasing. You can see that here. If you remember that after running in a steady condition, it was 16.8. Okay, it is set from a value here, almost 16.8 for 9 a megawatt, and now so far after about 10 minutes it increases to 17.3, and it is still increasing. We can maybe see also changes here to the temperature of the exit gas. We shouldn't see much because the output power is constant, but maybe changes to the steam cycle that we have it here. See, Now, okay, we are at about 18 seconds. The total time is about 20 seconds. So this is one of the loading scenarios for the plant. So we almost done. We done. Okay, 20 second. The power it is about 17.5.6. Okay, you can see that here. For the output power, and for the steam, this is for steam power. This is for the gas power. The total power received to the generator from these two it is 63.4, and the efficiency it is 28.8 percent. So in this video I just showed you how to use this power plant model available from Flownex team. The power plant, it is a combined cycle. It means that we have a gas turbine and we have a steam turbine, and we have a heat recovery system using in the boiler to make steam from the water and send out steam to the gas turbine. So we have combined outputs from the steam turbine and gas turbine, and this is where we can see the total output power and the efficiency. Many many components used here, okay, as you can see, and the way that you use it, you need to first initialize it with the snap that it is available, and then you will go for a steady state solution. Be sure that after running the steady state solution is that you have zero uh, energy source, because we don't want to have this non-zero energy source for optimizing the boiler system. And in this way I just use a designer, okay, that it is implemented. I just come here, go to the designer setup. The aim is to get zero energy source for that by changing the the design, and this is by changing the pressures here for pressure of the boiler drum. And after that we are ready to move on for transient analysis here. Transient analysis that we done it here, and we see that in these two graphs the output power for the steam generation and for the gas generation. And here we have some numbers that showing you what's going on about, like here for example for the gas turbine, for the output power, and steam turbines same, and also the temperatures during the gas exhaust, hot gas exhaust, that going and vented out to the ambient, and also at the same time hitting the water cycle here and converted that to the steam that needs to be sent out and used by the steam turbine. I have another video that I will show you how to change this mass flow rate for the input fuel, which is here a natural gas, and also have to consider the effect of the weather. Okay, these two parameters I'm going to change that and see that their effects on the overall efficiency and also the total output power for the power plant. Thank you for watching this video.